official. There we go. Okay. So here's what I want to show you. This is, click everything closed. I'll make this real quick, and then tomorrow you can have a data test, and then Thursday I think we can build it another day if you need to either work on stuff, if you're done testing, or test.
What should I title these notes?
So these notes, we're going to do sketching polynomials. Sketching polynomials. That's what we're talking about. Okay, this is and I'm going to show you something here that is really important. This sets the foundation for something that we do in calculus that is, in a couple of years, that's really unique to kind of the way I do calculus. And so this is, you're going to get your first glimpse of using what I call function tables to sketch a graph. And this isn't really high-level stuff, but I want to show it to you mainly because it makes it easier to deal with when we cover this topic in calculus. It makes it a lot easier. You've already thought about it a little bit, and it just works a lot better. So sketching polynomials. Really. Now, first of all, sketching is different than graphing. If we want to graph something exactly, we use technology, right? Sketching, we do a lot of curve sketching in calculus, and sketching is important when we're just trying to get an idea where the important features on a function are. So we want to know where the peaks and the valleys are, the extrema, we'll call it in calculus, the maxima and the minima. We want to know, where maybe x-intercepts are sometimes, some of the zeros. We want to know later on in calculus, we'll talk about points of inflection, which you have no idea what those even are yet. But all this stuff will show up eventually on this table that we're going to start building today. Now, at this level, the table we're going to build doesn't really have a bunch of calculus stuff. All it's going to have is we want to know where are the x-intercepts of the function and what does it do in between the x-intercepts. Okay, and there's a really simple way to get at this. Okay. So what if we want to sketch this function? Okay, f of x. So first of all, what are the zeros of this? Okay, so we've got, it's already in factored form. Now if it weren't in factored form, then you'd be doing all the stuff that you're just currently wrapping up from Unit 5 on how do we factor this thing to find the x-intercepts, to find the zeros, right? So that's all the stuff that you've already practiced. Well, let's just, at this point, I'm going to give it to you in factored form. Now you could get there, right, by, if it wasn't in factored form, by using the rational root theorem or using the factor approaches that we've taken, for 2, 3, and 4 term polynomials. You have a bunch of different methods for getting this thing factored, for finding the zeros. Okay, and we'll look at some of those, later. Later we'll look at some where we start with one that's not factored and we have to do the whole thing. But I'm not going to give you really hard ones to do like that anyway. So they're not going to be really difficult to factor. Okay, so here we've got this one that's factored. If I set it equal to 0 to find the zeros, what do we get?
2.
So I get 2 from that. If I apply the zero product property, the zeros are going to be x equals 2 or
0
or -3 from that factor, or 0 from that one, right? Okay. So now here's where we're going to make a table. Okay, so now we're going to draw a table, and here's what the tables look like. This represents the x-axis. Okay, here's the function. There's a row for the function, so the y values that go with. In fact, let's even just call it y. Instead of calling it f, let's just call it y, because y and f of x are the same thing, right? Okay, so first of all, the first word I'm going to throw at you is the domain. The domain of a polynomial. So that's a word we haven't talked a lot about, but we're going to talk more about in the next week. Okay, so what's the domain? What are the values of x that we could plug into that function? For a polynomial, it's everything. There are no restrictions. It's going to be always from -infinity to infinity. There's nothing we couldn't plug in there. What are the numbers, though? Just to get us thinking along these lines, what would be a case where maybe there'd be some numbers that wouldn't work? Well, there's really only 2 things to think about in math. Am I going to be forced to divide by 0, which I can't do, or do I have to take an even root, so like a square root of a negative number? So if I had a different function, like if I had something like, let's call it g of x equals 2 over x minus 3, and the next unit we're going to talk about rational functions, where they're going to be ratios where we get x's on the top and the bottom. What would be, just real quick, what would be the one value of x that we would have to exclude from the domain because it would force us to divide by 0? 3, right? Everybody see that? If x were equal to 3, I'd get 2 over 0, and that's one of the things that's forbidden. We can't divide by 0. So the domain of that function would have to be that x can't equal 3. But everything else would be fine, okay? But for polynomials, we don't even have to worry about that. Polynomials, there's no x's on the bottom, there's no radicals, so everything is fair game, right? So the domain is going to go all the way from negative infinity up to infinity. And doesn't that just look like we're using interval notation, right? I've got the rounded brackets from infinity, negative infinity to infinity. Everything is fine, okay? The three numbers that we get that are the zeros, though, we know what those are. So we get 0, we get -3, 0, and 2, right? And those are zeros. Because those are zeros, we know that the y value at each of those places is 0. Okay, so you get an idea how this table is working. We've got the x values in the first row and the corresponding y values in the second row, right? So these sort of look like, and you can treat these like they're ordered pairs. They're just turned sideways now, right? So there's an ordered pair, there's an ordered pair, and there's an ordered pair. X values and y values. Oh, so we know these are the x-intercepts. So if we were to start graphing this thing, here's what it would look like. Right, there's the x-axis. Here's going to be the y-axis because that's where x equals 0. Everybody see that? And these points would just look like there, out at 2, and back at -3. We've got x-intercepts. We just need to know what happens in between, right? We know that the function's going to be crossing through the x-axis there, or at least touching the x-axis. Does anybody have an idea how we could figure out what's happening in between? We're going to pick test points, what we'll call those. We're going to pick test points in between the x-intercepts. Have you ever done anything like this?
Right now.
First time? Okay. So we're going to pick some test points. Like a convenient test point here would be 1, wouldn't it? Right? So we'll pick a test point at 1. Out here we could pick a test point at whatever, something bigger than 2 and less than infinity. How about 10? Between -3 and 0, so let's pick -1. Let's pick -1 as our test point. And then back here, like maybe -10. You know, the nice thing is, we don't even really need to know what the y values are. All we care about is, are they above or below the x-axis? So really all we care about are the signs of the function there. So here's our function. There's f of x. It's already in factored form, which makes it really easy to work with. What if I plug in something like -10? So I'm going to erase this stuff. We'll do that for now. So what if we want to do something like f of -10? All we got to do is look at each of these three factors and determine are they positive or negative, because I've got a product of factors. And by knowing the signs of the factors, we can know the overall sign of the function. So at -10, what's the sign of that factor? Positive or negative? Negative. So I'm going to get a negative times, how about there? -10 minus 2. Negative. How about that one? -10 plus 3. What's the result if I do negative times negative times negative? Negative. I have an odd number of negative factors, and so the overall result is negative, right? Okay, what about at -1?
Negative.
First one is negative. Second one is negative. Third one is, so the overall sign is positive. I have an even number of negatives, right? So I get a positive. Okay, how about f of 1? Positive, negative, overall sign. And then if I go up to 10, they're all positive, aren't they? Right? Okay, so then look what's happening here. Okay, so that means that somewhere in between it's positive. So I don't even care where it is, but I just know it's going to be up there somewhere, right? With a sketch, I don't care how high it goes. I just want to know, is it above or below? Over here between 0 and 2, it's negative, so it's down below. Out here to the right, it's above. Out here to the left, it's below. So what does this function have to look like? Yeah, it's got to just do, doesn't it have to do something like, oops, I missed it. Missed it by a mile. I don't know what I was doing. Yeah, that's not good, is it?
I would just kind of swoop it.
Yeah, so maybe that was down here further. So it's just going, it's going up.
What was that point down there?
Oh, I kind of picked a bad point, didn't I? So it looks something like that, right? Okay, that's our polynomial. Is it exact? No. Is it very pretty? Not really. But you could probably draw a prettier one.
Yeah.
But you get the idea. That's what it has to do, okay? So now, this is a third degree polynomial. Think back to the fundamental theorem of algebra. What's the maximum number of zeros we could have? 3. They could all be real, right? So the maximum number of x-intercepts we could have is 3. Okay. This one had all 3. Did it have to? No, it didn't. But it could have had up to 3, and it did. Okay. We call these places turning points. Peaks and valleys are called turning points for us for now. Okay, later on, we'll call them extrema. If I have 3 x-intercepts, what's the maximum number of turning points that I could ever have? What do you think? What? Say it again. 2. How come? Because it's. Would you agree? It's got to turn around to go back through the x-axis, right? So it's got to turn around twice. But why couldn't it maybe turn around out here somewhere?
Because it have another 0.
I'd have to have another 0, and I can't have another 0, right? Okay, so we learned something important here. I mean, one of these things we already knew. The maximum number of x-intercepts is always going to be the degree of the function, the degree of the polynomial. The maximum number of turning points is always going to be 1 less than that, isn't it? Right? It's got to turn 1 less time than the number of x-intercepts. Agreed? We may not get all those. We may not get all 2 turning points or all 3 x-intercepts, but those are the maximum numbers. Okay? Last issue. So the last issue here, I'm going to use a little bit of calculus terminology, so pay very close attention. I know I got like just a minute here. So what happens, we talked about this earlier in the year a little bit when we talked about as x approaches negative infinity, we would have said it like this. As x approaches negative infinity, f of x approaches blank. Okay, in this case, wouldn't you agree it's going to be negative infinity based on what we learned earlier? Okay. So what we call this in calculus is we call that a limit. It's a limit because we're going to go, we can't ever get there, but we're going to go as far as we can to the left and see what the function does there. You know, we can never get to negative infinity, but we can kind of know what's the limit of the function's behavior as we go that way forever. And the answer is negative infinity because it goes down after that last x-intercept. Agreed? What about on the other side? If I take a limit of the function, as x approaches infinity, I can never get there, but what's its behavior? It approaches infinity, right? Okay, so we could fill in those blanks then. Over here, if we wanted to say something like, as x approaches positive infinity, f of x approaches infinity, right? Okay, and that's pretty much all we need to do to sketch a function. I want to look at a couple more examples. So we'll look at some examples on Wednesday, and I'll give you Thursday will be a day to kind of, so we'll test tomorrow, and Thursday I'll open up a day for you. Okay? Yes, I'll be here 7th period.